Well, I don't have anything to lecture about. I'll just take your questions. And my TAs are here too. They'll help me as well. Who wants to be the first brave person to ask a question? Yes. Okay, it's a question, that's right. That's going to be similar in structure. In length, hopefully it'll be shorter, but it's not clear how much shorter it will be. It's not good. So it's not, as I said in class, you're responsible for any material. There could be stuff from the first exam, but most of the stuff will be from what we covered after the first exam. Say it again? There will be, but the focus will be on the second part. So you don't need to know everything from the previous part. But you should still know, because in the final it's going to be comprehensive, right? Don't forget basically what you... that's right, yes. If you had to make a choice like that, you missed it on the second part. I don't know, yes, perhaps. I don't know. You guys are trying to get the questions out of me, but I don't think that's going to be the best time to spend the time. You should know how to word execution. There you go. Yeah. Yeah. So, what else? Any? Okay, that's a good question. What's the difference between VLIW and superscalar out of order? Well, superscalar and out of order are different things, right? So you said three different words. VLIW.
What if superscalar and out of order
used together? Superscalar plus out of order. That's what you're saying. So VLIW is an execution model where you put multiple operations in a single instruction, right? Very long instruction words. And the compiler finds which operations can be executed independently and packs them in this large word. So it's a statically scheduled machine, if you will. That's the major difference, right? This is compiler finds independent operations and packs them into a word, the instruction word, and the hardware simply executes them without any dependency check. The execution is lockstep. If any of those instructions is blocked for some reason, all of the instructions in the word gets blocked. A superscalar is another way of executing multiple instructions per cycle, right? Except here the burden is on the hardware. The hardware fetches n instructions per cycle, and it needs to detect dependencies between those instructions to figure out whether or not those can be executed concurrently in the same cycle. Now, out-of-order execution on top of that adds dynamic scheduling, right? Meaning, if an instruction is stalled for some reason, another instruction that's independent that comes later in the instruction stream can be executed. Right? Hopefully that's clear. Yes?
So, how is superscalar different from prefetching?
How is superscalar different from prefetching?
Prefetching instruction.
So that it's a prefetching instruction. So those are different concepts, right? Superscalar execution is multiple instruction, fetch, decode, execute. Essentially, you have multiple pipelines, right? You fetch instruction 1, 2, 3, 4, and execute them. Fetch them concurrently, decode them concurrently, execute them concurrently. Prefetching is something that happens from the I cache, from the next level of memory into the I cache, right? Second level cache to I cache. Does that make sense? So they're totally orthogonal concepts. There's no relation between them.
Does VLIW also have concurrent execution?
That's right. VLIW is another way of fetching, decoding, executing multiple instructions, except the compiler guarantees that those instructions that are in the long instruction word are independent of each other.
So basically, the difference between superscalar and VLIW is whose program it is to figure out what's dependent.
Exactly. Yeah, that's the major difference.
And you said that VLIW can find this action structure that they all be executed.
That's right. Exactly. If one instruction stalls, all of the instructions in the long instruction word also stall. This is the strict initial VLIW engines. That's the concept. Yes?
Can you possibly go over the memory problem in homework 5?
Memory problem in homework 5. I don't even remember that.
It was basically one bits I used for.
Okay. This may be a good question while I eat. Let's see. This is the
This is where you have to determine like the bits, so like where they say.
yeah, this is where you have the ranks, right? Homework 5. Can we project here? Or should we project here? Does everybody have the problem in their hands? Or? Oh, I do have the numerical. That's what we need.
I want to make sure that I come with it.
Well, I think you'll take
Basically, what I'm really
but yeah, I know.
I guess I was thinking between chips and banks because
Okay.
And I like the places.
the way this problem shows it, it's sort
It's
of,
weird. It's like there's a really.
I sort of understand that chips, in one bank are multiple chips as opposed to the lecture slide suggest that one chip is made of multiple banks.
One chip is actually made of multiple banks.
Yeah,
That's
but
right.
that lecture seems, I mean, if you just go down,
So this is a logical organization of memory, right? That's the thing to realize. In this picture, you see a logical organization, right, Malaya?
Yes, and I guess what they find confusing is further down.
yeah.
Okay, let's go further down.
That one.
Yeah, a more detailed picture.
It says a more detailed picture of the memory chips in bank 0 or bank 0, which seems to suggest that bank
Yeah.
0 is made up of memory chips.
That's right. So this is an unfortunate. Well, bank 0 is actually made up of many chips, right? Bank 0 is distributed across many chips. So let me give you the picture. So what you have in a memory chip is, this is the chip. You have 8 banks. I don't know how many in this case. I guess there are 4 banks here? Or?
Eight banks.
Okay, 8 banks. So what you really have is bank 0, bank 1, bank 2, bank 3, bank 4, 5, 6, 7, right? 8 banks. And these all share the address, command, and data buses, right? As we discussed in class. And only one of them can use the address, command, and data bus at any given time. And they supply 8 bits. I'm not talking about the question right now. Conceptual view. Now, what you do in a rank is you take multiple of these chips let's say you want to form a 32-bit wide interface. I think it's a 32-bit wide interface in this case. You take 4 of these chips, 1, 2, 3, 4. So you can imagine the other 8 bits coming. And form a wide interface. Basically, you have a 32-bit wide interface. And each chip supplies 8 bits. So if you look at this chip, you have bank 0 also. So how do these operate? Basically, when you send a command to get 32 bits, you get 8 bits from bank 0 of chip 0, if you will. You get the next 8 bits from bank 0 of chip 1. You get the next 8 bits from bank 0 of chip 2. And you get the next 8 bits from here. Does that make sense? So bank 0 is actually in different chips because of the rank you formed.
So,
You logically operate those chips together.
So a particular bank is distributed across many chips.
Exactly, yes. Exactly. Because of the wide interface. Is that clear now? Does that clarify the question? I don't know why this turns off. Yes? So the rank is this. The rank is all of this. This is one rank. So a rank, what is a rank? It's a set of chips that correspond to the same command at the same time with different data. Okay. So you tell all of the chips to activate in bank 0, and they activate. Except they do it on different pieces of data, right? Different 8 bits, if you will. Yes?
So if I have a channel that has like 2 DRAM chip things, does that mean that we partition like the address space between the different chips?
What's a DRAM chip thing? 2 ranks, you mean?
No, the thing. So the channel has the different set of channels.
Yeah. Yes, that's right. You do a partition of the address space.
Okay.
I mean, you could use any data mapping mechanism between them again, right? It really depends on which bits you use to select the div in the address.
Is it also common to like take different divs as like a rank and have one of them like have half the bits and another div have half the bits?
Then they will be ranks, right?
Yeah, but like is that
That's-
Multiple ranks are in one data. One name has multiple ranks.
That's right, yes. That's right.
Multiple names make up one.
That's right, exactly. I mean, it could be done. There's no reason why it cannot be done, right? You could take different DIMMs and operate them in lockstep, if you will, just like a single rank, right? But it's normally not done. To answer your question.
So banks are more granular than
Ranks are more.
they're
That's right, yeah. So let me actually open this lecture again. If I can find it. Or maybe. Does it make sense? Cache that main memory. Okay, let's. Okay, so I would recommend studying these lecture notes because these clarify. Say it again. You want to go through the lecture again?
No.
Okay, not here. I think it's the 19th. After lecture. So if you look at this, this is the DRAM chip, right? You take DRAM chips, and this is exactly what I've done over there. You have 8 of these instead of 4 here, and they supply the data. So this is one rank. You could have another rank on the other side of this div. I think we have some pictures like that. Yeah, exactly. So there are 2 ranks, if you will, here in this DIM. Okay?
You each DIMM has one channel.
In this case, each DIMM is connected to one channel. That's right.
The chips are not shown.
The chips are not shown.
The banks are.
Well, yeah, that's. You can look at different pictures, but this is the hierarchy basically. You said you start with a cell. Actually, maybe I should put the cell here. You have a row of cells, and you have columns of cells, two-dimensional array of cells, and that forms a bank, right? And a chip has multiple banks, and you take multiple chips and operate them as a wide interface, as a rank of soldiers. And then you have multiple ranks that form a DIMM, and a DIMM is connected to a channel, or multiple DIMMs can be connected to a channel also. But you don't need to worry about that. Okay? Okay, yes?
Can't this just be simplified as, row column and they just have numbers on top instead of having, names for things?
Numbers on top instead of what do you mean?
I mean, just have row column and just have, level 1, level 2, level 3.
Yeah, you could think of it that way. You could think of it that way, certainly. You could think of it that way, because essentially what you're doing is putting these things together to form a bigger memory system, right?
So they're usually.
So in this module, banks and chips can be switched, right?
Banks and chips can be switched. No, multiple banks comprise a chip, right?
Multiple chips have multiple banks.
Yeah, so that's the way you operate a rank, if you will, right?
Yeah.
Yeah.
So multiple chips have multiple banks. They're kind of at the same level.
That's right, yeah. If you operate them as a rank, that's right. You're absolutely right. So in a sense, there is no hierarchy in that case. You just need to know how it works. Right? As long as you know how it works, you don't need to assign names to it, if you will. Yes?
When you're talking about a cache and you have both the tag and data store, are those two separate entities, or is it just that they're next to each other, and if the tag matches, then you take the data? Because I wasn't sure how they're organized in terms of, are they two separate memory blocks?
Yeah, normally there are two separate memory blocks. So you have a memory block for tag store. Although I guess one could imagine having them the same memory block, right? There's no reason not to be able to do that except for access latency and cost reasons. I don't know how to manage these things. So a tag store, normally you have two different blocks because data store is very regular, right? You have, but if you will, the indexing function is the same for both of them. Does that make sense? But normally, if you look at a chip, they're organized as separate memory blocks. But they're both memory.
And then the tag store will output a hit, and then that means you use the output of the data store.
Exactly, yeah. So we've discussed multiple types of access. So if you get an address, you use the index bits to index into both. Tag store outputs a hit or miss, and you know what that hit or miss is, right? If the data you're accessing is valid, and if the valid bit is set, and if the tag that's stored here matches this tag, so you compare this and then AND it with the valid bit, that's the hit miss signal. Then the data coming from data store is valid. You can use that. And when you have an associative cache, you do multiple of these tag comparisons in different ways. And the way that matches, you select the data from the way that matches. Make sense? Okay. I hope everybody's all right outside. Does that answer your question? Okay. Yes.
Virtual addresses, I guess, are they considered addressable? What I mean by that is sometimes ask you about what's the size of the virtual address space. I wasn't sure if like the virtual address that they're giving you is in reference to like bytes.
So that should be specified, right?
Well, right, so it should be specified.
Yeah, it should be specified. For byte addressable, I mean, a virtual address, addressability is orthogonal again to exactly to what's the reference. Addressability is specified by the ISA. And you could have a byte addressable ISA, in which case the virtual address that you generate in a load or store is an address with a byte in memory. You could have a word addressable ISA, or word addressability mode, if you will, in an instruction. Then the virtual address you get will be a word address. What else? Hopefully you guys have a lot of questions. So I'll wait for your questions. I don't have any questions to ask. I'll ask my questions on Wednesday. No, nothing? Yes?
Can we go over like scheduling policies, sort of for scheduling DRAM accesses?
Sure. So, what do you want to go over in particular? All of them? Or?
I don't really know. I just don't really remember that too well.
So, I guess I'll give you a high-level overview. So, we discussed several scheduling policies. One was first come, first serve, right? This is, in a sense, the simplest scheduling policy you can ever have. Whatever arrives first, service that next. That's simple. Hopefully that's clear, right? The other scheduling policy that takes advantage of the structure of a DRAM bank is first ready, first come, first serve, or row hit first scheduling policy. Here you have two priority levels. Basically, first you prioritize row hit accesses, and all else being equal, you prioritize the older accesses. Okay. So the idea here is you have this row buffer in DRAM, and if your access hits in the row buffer, service those accesses first. Why? Because that takes much shorter to service than an access that misses in the row buffer. Okay. So if you service those accesses first, then you minimize the latency of access. Also, you maximize the data throughput you obtain from DRAM, because you're getting more bits per cycle, if you will, bits per second. So that's the idea. You prioritize row hit accesses, and if there are two row hit accesses for the same row in a bank, then you pick the older one. If there are no row hit accesses, then you pick the older one. And we discussed, the goal of this is to maximize data throughput, DRAM data throughput, DRAM data bus throughput, if you will, and minimize access latency also. And you can go through the DRAM bank operation that we've gone through a couple of times to understand why that happens. So the issue with these policies, when you have them in a multi-core system, is now you have multiple applications sharing the memory controller, right? This is your DRAM controller. And you have, let's say, two cores. Core 0, core 1. They will share the memory controller. Now, if your policy is like this, or like this, you could starve an application for a while, especially if it's like this. Why? Because the memory scheduler can prioritize row hit accesses, and an application can always be hitting in the row. It could always be generating accesses that hit in the row, and the memory scheduler could always be prioritizing that application or that core that's running that application. So this is prone to starvation, or for a number of cycles you can starve another application. So to prevent this, we've looked at some policies that try to provide fairness to different applications. that are sharing the controller. And one idea was stall time pair memory scheduling. You guys remember this? So the idea here was, I'll give you the high-level idea. You can go through the slides or we can go in depth later on. The idea is estimate the slowdown each thread or each core or each application experiences compared to when it's run alone. And if unfairness is greater than some threshold, then prioritize the application that has been slowed down the most. So the controller, what does it do? The controller estimates slowdown of each core, let's say, and then it calculates an unfairness value, which is the max slowdown of any core divided by minimum slowdown of any core. And if this unfairness is not tolerable, let's say greater than some threshold, then the controller uses this scheduling policy. Basically prioritize requests from the core that has the max slowdown. Now what does this mean? Unfairness is bad, which means that you've slowed down a core too much. If you prioritize its requests, its slowdown will go down. Okay. Does that make sense? Yes, you have.
Yeah, for when it's calculating the slowdown, does it calculate using the FCFS or the FRFCFS, or which schedule it's currently using? Right? How does it calculate slowdown?
Oh, so when it calculates the slowdown, basically, how does it calculate? I don't want to go into too much detail because you don't really need to know the exact detail. But the idea is you slow down a thread compared to when it's run alone if the scheduler picks another thread's request, another core's request over this core's request. Okay. And whenever this happens, you increment a counter, if you will, a latency counter that says, for this number of cycles, I service some other thread, some other core. Whereas if that core was running alone, it would have continued. So in a sense, it doesn't matter if it's FRCFS or FCFS. Although you don't need to know the exact implementation details of how this is done. Just know the basic idea of how the schedulers operate. So if unfairness is greater than the policy is prioritize the request from the core that has the maximum slowdown. The second level of priority is row hit first. Again, prioritize row hit first request, and third level is oldest first. If unfairness is else, I'll say, if unfairness is tolerable, then we use row hit first scheduling policy again. Because unfairness is tolerable, unfairness is not a problem. So why don't we maximize DRF tuples? Okay. So why would we want to do that? Why would we want to? So if you take a step back, the goal here is to balance the slowdown of applications, keep the slowdown in check. Whereas if you look at this, here one application can slow down a lot, right? Because it can starve for a long time. Here, the scheduler prevents that. Make sense? Yes?
Shouldn't the unfairness be based on priority of the equalness of the task?
Yeah, so assume that all of the tasks are equal priority in this case. We didn't go into how you handle priority. There are ways of handling it. And I'm happy to talk about it maybe during office hours. Right? Or you can read the paper. But that won't be on the exam. But if you want me to talk about it, I can talk about it. Okay, so we also covered another scheduler, right? Which is the parallelism aware batch scheduler. So the problem happens because threads interfere in the memory system, and you need to have policies that reduce that interference, if you will. And this is what STFM is trying to do. You've covered another way in which threads interfere with each other in the system, which is they can serialize each other's requests. Do you remember that? Maybe I'll show you the picture again briefly. Main memory. It should be here, right? No, it should be here. Memory space. Okay, should really look at this lecture. Okay, remember this picture? So if a thread has two requests, they can be serviced in parallel in different DRAM banks, right? And that way the thread stalls for one bank access latency. That's the notion of memory level parallelism. You can generate two requests, and as long as if they go to different banks, they can be serviced in parallel. But when you have two of these threads together, they can interfere with each other. What might happen is the controller actually serializes both of the threads' requests. It services thread A's requests in serial and thread B's request in serial also. You can go through this animation on your own. Yes?
Don't you need multiple channels to service multiple requests on two different banks also?
Don't you? Well, you can service requests at the different banks, except the data needs to come out in different cycles. So when you access a bank, what does it take? You need to activate the row, and you need to do a column access. Those things can be in parallel in different banks,
Right.
until they need to use the data bus. That part cannot be in parallel.
Does database take only a single cycle? Or is that pipeline?
It could take multiple cycles. In fact, in your lab assignment, you will do many cycles. But that could be pipelined also. Okay? So in this case, data bus takes some number of cycles, as you can see, right? But it's not as high as the amount of time it takes to access the bank. Okay? But the same concept is applicable across channels also. So here, what happened is the scheduler essentially serialized each of these threads requests because it didn't try to service them in parallel, right? Try to service the thread request in parallel. As a result, you got two bank access latencies for each thread. So you can do better, and that's the idea of parallelism over batch scheduler. We realized that if you prioritize one thread over the other, you could service that thread's request in parallel, and that thread now can go back to its computation. Do you guys remember this slide? Okay. Now that thread can compute, this thread stalls, but it doesn't stall more than it would have stalled up there. So in the end, you can save some cycles on this particular thread, continue executing. And that way you can reduce interference. So that was the idea on which parallelism over batch scheduler was built. So how do you build this? We talked about two key principles, right? Principle one is parallelism awareness. Basically, schedule a thread's request to different banks back to back. But then this can cause starvation. So why don't we batch the requests to ensure that no thread starves? Basically, the scheduler forms a batch of requests out of all of the requests in its queue and inserts into the batch only some number of requests from each thread. And then forms a ranking within that batch and serves the threads based on that ranking. So what does ranking enable? Ranking enables you to exploit this parallelism. What does batching enable? Batching eliminates starvation. It provides fairness. And you can go through this animation. Does that answer your question? So this was the most sophisticated scheduler we examined. And there are two key principles, basically. One is batching to eliminate starvation and provide some fairness. And the other is ranking within a batch, thread ranking. And the idea here is to, well, there's a particular way threads are ranked. The threads that have shorter stall times are ranked higher, which means the threads that are less intensive in terms of memory, that will finish soon, are ranked higher because you want to service a shorter job, if you will, first to maximize system throughput. So this is rank threads with shorter stall times higher. So this way you actually preserve each thread's parallelism as much as you can. So you don't serialize the thread's request because you're servicing each thread's request back to back. And you also improve system throughput. Why? Because you're prioritizing those threads that have fewer requests. Right? If a thread has only one request to a bank, it's ranked higher because the stall time is short. Right? It needs only one request to be serviced, as opposed to 10 different requests. Now, when you add through this example, you can go through these slides. This explains all of these clearly, I think. Remember, we ran through this example, how PowerBS would schedule requests, how it would form the ranking based on these values, how it would form the load of each thread on each bank, and I guess this is the baseline order. Basically, in the end, by ranking the threads, I'll just open all of this. This is the scheduling order with PowerBS. Because the baseline mechanism doesn't rank the threads, what you get is different banks service different thread requests at the same time. Right? Whereas once you rank the threads, once you say thread 0 is higher priority than thread 1, is higher priority than thread 2, is higher priority than thread 3, this is the kind of regular service order you get in the banks. So thread 0, for example, all of its requests are serviced in parallel, except for the data bus part. Make sense? Okay. So those are the 4 different scheduling policies we talked about. Yes?
Can you talk about the 2 different CMU processors?
I see. Sure. 2 different SIMD processors. If I can find, I don't know how you would do this. Like a puzzle. Oh, this doesn't move. How are you supposed to access that, I guess? Okay. Oh. Still, there's some occlusion that happens here. But it's better than going up, you're right. Okay, 2 different processors. Array processor, so SIMD, single instruction, multiple data. There are 2 different ways of doing it from a purist point of view, array and vector. And the idea in array processor is you execute, basically you execute the same operation on multiple data elements concurrently at the same time, right? So if you look at an array processor, it's like this. You have processing elements. That can do, let's say you're doing an add of 2 vectors, right? Let's say you have vector add, vector store into vector 2, vector 0, vector 1. What happens is all processing elements do the add at the same time on different elements of vector 0 and vector 1. This one does vector 0, 0, vector 1, 0. This one does vector 0, 1, first element, vector 1, 1, and so on. And all of this happens concurrently. That's the array processor. Same op at the same time on different data. Whereas vector processor, what happens is you execute the same operation on multiple data elements again That's the idea, single instruction, multiple data. In consecutive cycles. Right. You can have only a single processing element in this case, right? Single processing element that does something. So how does this vector add execute on a vector processor? Basically, in the first cycle, you take the first element and generate the result. In the next cycle, you take the next elements from the different vector. In the next cycle, you take the next element. You asked the question, right? Does that make sense? So it's really, do you do the same operation at the same time or in consecutive cycles? And if I go back to this picture, you'll see the time-space duality a little bit more clearly. Let me just show you that, if I can find it. Is it this one? It looks like it, huh? You will be able to get to it. Oh, it's not here. I think it's in the second concurrency lecture. Okay. Yeah, if you look at this, this is essentially showing an array processor. Each processing element can do everything, and you do the same op on multiple elements at the same time. You do 4 loads on 4 different elements, and 4 adds on 4 different elements, 4 multiplies on 4 different elements, 4 stores for this program. Whereas a vector processor, you do the load of the first element in the first cycle. In the next cycle, you do the load of the next element and add of the first element, and so on. And that's the time-space duality. If you look at time, you do the same operation at the same time in an array processor. Whereas if you look at time, you do the different operations. You do different operations at the same time in a vector processor. This is the time. If you look at space, space is what processing element does what. You do different operations in the same space, so your processing elements need to be powerful. Whereas here, you do the same operation in the same space. So this is a less costly machine because you're pipelining operations over multiple cycles. Here you're not doing multiple loads at the same time, right? And you could have a pipeline load unit, obviously, but they'll be on different stages of load unit. Yes?
Sorry, which one did you say was more costly?
So if you look at this, what do you think? This is more costly, right? Because you need to have 4 load units, you need to have 4 add units, you need to have 4 multiply units, and 4 store units at the same time. Whereas here you can get away with 1 of each. Because you're not operating on the different data elements at the same time. You're just pipelining the operation in consecutive cycles. Yes?
I have a question regarding kind of like data flow.
Okay.
Do we have to know more beyond just like the nodes, or should we also know like all the different implementations, like those in Manchester and all this weird like algorithm?
No, you don't need to. You need to know the basic operation of a data flow processor, but you don't need to know all the different implementations.
Okay. So
you
we wouldn't need to know like instruction packing, just as long as we could like interpret some type of graph.
No, now you're asking specific questions. You need to know how a basic data flow processor operates. Like what needs to happen to execute an instruction in a data flow processor. But I'm not going to ask you what's the difference between Manchester machine versus MIT's tag token data flow machine, because we didn't cover things into that detail. So you need to definitely know the concept of data flow and how a basic data flow processor would operate. Okay? Yes?
So the only difference between a vector processor and like a regular pipeline that we've been studying so far is that in the vector processor you're operating, like every operation that you do is on like a vector as opposed to a scale.
That's right, exactly. And that's why you can pipeline these things deeply, as we discussed in class, right? Because every pipeline stage can be operating on, like you can have a 1,000-bit adder, if you will, and all of the stages in the adder will be operating on a different data element, which means that they're by definition independent.
So you're operating on like 60 parallels or something like what is.
That's right.
Okay.
Okay.
So if I wanted to do another add after the add there, would that mean that all those multiplies that became adds would have to shift down past that add word?
That's right. Yes. So if you need to do another add right between the add and multiply, you're saying.
Yeah.
Yes. Which means that you start the next add right here, and next multiply starts here, and then store starts here.
The adds multiply.
Wait, you can.
You need to have two adders. Sorry. That's right. What I said assumes two adders.
But what if I have a single adder? Then do they shift down?
Yeah. Then they need to shift down, I think. Yes.
Because you can't do it at the same time.
Because you have only so many pipeline stages, right?
Pipeline,
Yeah.
nothing you want out.
So you will need to add another adder. Absolutely. Yes.
So the main benefit, I guess, of vector processors is just getting rid of like having to actually like load the instructions. So,
Wait, compared to what?
I guess compared to just
Well, compared to a scalar processor, there are multiple benefits, right? You fetch a single instruction, decode a single instruction, and it specifies many operations at the same time. So you reduce the overhead of fetching and decoding many instructions. And then you also exploit the parallelism, right? There are multiple benefits. Like this pipelining is not possible in a scalar processor. Just because you know that you're operating on vectors, you can do this kind of deep pipeline. Yes?
Along these lines, we also talked about CPU.
Okay. Sure. So let's go to those slides actually. So what's a GPU? A GPU is essentially an array processor, except it's programmed in a different way.
Can you explain thread warps again?
Oh, can I explain thread warps? So thread warps. So let's take a look at this example. This will give you an idea of what a thread warp is. So this is a vector add, right? You're adding vector A and B and storing the result in C. One way to express this operation is using vector instructions that you did in your homework and we did in class. Like vector add this. Vector add, I don't know. You need to do a vector load of A or vector load of A into vector register 0, vector load of B into vector register 1, vector add vector register 1, vector register 2, store the results in vector register 3, and then you do a vector store. That's one way of programming this on a regular vector machine. Another way, the GPUs are essentially the same principle, except they're not programmed this way. The way they're programmed is somebody realized at some point that, oh, these threads, you can express this as a kernel, this is the kernel, right? You could actually write this as a scalar program, right? You don't do a vector program. You still do just load, well in this case it's load, add, store. Load, add, store. You don't have a vector program. You have a scalar program. But you can execute these scalar programs in parallel at the same time. And they happen to be executing the same code because they're operating on multiple data elements. So what a thread warp is a collection of these scalar threads that exactly do the same thing, except on different data elements. So if we go back to the previous slide, that's what it is. Right? You have scalar threads. They're all doing the same thing. Remember this load, add, store. They happen to have the same program counter at the same time. Does that make sense?
Doesn't that need like a lot of machine
Yes, it's an array processor. That's why, right? Exactly. That's why it's an array processor. Remember the array processor?
Right.
Same operation
Right.
on multiple data elements at the same time. That's what's happening here.
And that make it very expensive.
Well, yes, it's more expensive than having a single adder. That's right. Or having a million adders are more expensive than having 64 adders. But still, I mean, if you want to get that kind of parallelism, that's the cost you pay. At least you don't do the decoding and fetching of the instructions, right? Because you have the common program counter. You can fetch the instruction once and distribute it to different units. Distribute it to the different adders, if you will, or load units. Yes?
So do they like fetch while they're doing like an array operation? So like I say I have an add and a multiply, and I like do my add and refetching my multiply.
That's right, yes. You can pipeline all of those operations.
So basically like the fetches just go away.
Exactly. Yes. So it's just like an array processor. The idea is essentially an array processor, except that you don't use vector instructions. Right? You don't use, the programmer doesn't need to specify vector-like vector instructions. They program like this, just like you would be programming a scalar machine. There's a little bit more to it. If you program the GPU, you will see that. But the fundamental principles, underlying principles, are the same.
Do you fetch only one instruction? Or you have to fetch as many that you have instructions for every
Well, they all do the same instruction, right? So you have a program counter. For this is your scalar thread. This is the program counter. I don't know, take 50. It's the exact same instruction, except that gets distributed to different data elements. So only your data operands. You need to fetch different data operands. Okay.
So what makes this not just a syntactic transformation of like vector code to GPU code?
Well, that's it basically. I would say there's nothing fundamentally different in a GPU than an array processor compared to an array processor. It's just how it's programmed. And you can look at some of these code examples. So well, that's the CPU program that we don't have but you can imagine the vector program over here, right? So if this is a CPU program, I guess this is adding two matrices together. This is a GPU program adding two matrices together. The kernel is the same. There's some additional thing that distributes the indices to different threads. But you don't need to really know about it for the purposes of this course, how to program it. If you look at the units, it's essentially you're fetching one instruction, decoding it, and different operations are executed in parallel, just like an array processor.
I'm like back to the top part of it, like the thread work. So like, does this seem to mean that like are you only fetching for one thread work at a time? Or?
That's right, yes. Because one thread warp, one program counter, right? And you have multiple thread warps that have potentially different program counters, and you can pipeline them.
Wasn't that wait? So if you're alternating between a lot, then isn't that bad for memory? Like I read a PC for one thread warp that's at some random place, then I'm gonna recipe for now I'm gonna fetch something for my next thread warp, so I'm gonna read like some different routing somewhere else.
Well, it depends on the size of your iCache, right? You could be fetching different instructions, that's right, for different thread warps.
Well, how related are they? Like, are they totally different programs?
So, in a GPU, actually, it's the same program. In fact, they could be executing the same program counter also, different thread warps.
So is that just...
So you might have, for example, 1,000 elements vector adds, and you divide it into. So you have a width of the machine, if you will. You can think of this as your vector length or array length at the same time. Let's say this is 32. Let's say you have 32 ALUs. You can do 32 adds at a time. But if you need to do a million adds, then you divide that into 1,000,000 divided by 32 thread warps. So you'll have lots of thread warps doing the same thing.
So could I also have some other unrelated tasks?
Not an existing GPU.
Okay.
Not an existing GPU. But again, that's nothing fundamental, right? That's just the way GPUs are designed today. You can certainly add multitasking to a GPU. But today it's not done that way. In 10 years from now, I'm pretty sure it will be done that way. Okay, what else? You guys like GPUs, I understand that. Maybe you should take my next course. Yes.
Can we go over misstatus handling registers? MSHR?
Misstatus handling registers. Okay, what do you want me to go over? What is the idea?
Yes. Yeah.
So what is the idea of a misstatus handling register? Basically, the idea is you want to have more than one outstanding miss at a time. So how do you support that? Keep track of what misses are outstanding. And that's the main key idea. I guess at some point I'll figure out how to do this.
Is this outstanding on the caches or outstanding in the memory?
Outstanding on the caches or in the memory? It's from the cache, right?
So when you're loading the cache.
Yeah. So let's say you have one cache. The processor requested address A, and it's not here. Cache block A. Let's call this cache block A. It's not here, and cache started sent a request downstream requesting address A. Now let's say the processor wants to do address B and address C and address A again. Right? If you have a structure that keeps track of the outstanding misses, you can do all of those in concurrently. Does that make sense? That's the idea of misstatus handling register. Basically, it makes the cache non-blocking. You record which misses are outstanding in the structure called the miss buffer or MSHR. And basically fill the cache when the misses come back from memory. Is that what you wanted to go into, or do you want to go into how it's structured?
How it's structured.
So I guess I'll show you the lecture notes because that's probably easier to do. Where did we cover this? Do you guys remember? Caches on main memory? Yeah, I think this one. Looks like just recognize that. Yeah. Okay. I already told you this, right? Basically, when you have a next cache act, so when you get a cache miss on A, you record in the structures that you're waiting for A. A is outstanding. And when B comes in, you search the structure to see if there's already a miss outstanding to B, if B is being serviced from the underlying levels. And it's not, so you allocate an MSHR entry. And then when C comes in from the processor, again, it checks if C is already being serviced. It's not in this case, so C is allocated an MSHR entry. Now let's say the processor wants to access block A again with a load instruction. Now A is already being serviced, which means that you don't need to send another request downstream because you've already sent and you're waiting for A. You just need to append the ID of the load, if you will. Let's say that's a load instruction to this MSHR entry, misstatus handling register entry, saying that when A comes back, provide this data to that load that requested it. And how do you do that? Basically, if you look at the structure of an MSHR, it looks something like this. is this one entry here. Is the entry valid? What is the block address, cache block address that we're waiting for, that is being serviced? And is this issued to memory, issued to the next load? And for each entry, you can actually store what load and what store is waiting for that, because this could be load, one of the loads that requested A, and this could be another load, right, that requested A. And they could be different parts of the cache block, right? Remember, a cache block is 64 bytes, at least. Could be 64 bytes. And different loads could load different portions. When the cache miss comes back, if this structure keeps track of which load was waiting for which portion, it can directly supply that portion back to the processor. That's the idea. That's why you have different sub-entries, if you will, for different loads and stores. How is that what? Well, this is the control logic for an L1 cache, right, to handle outstanding misses.
How are you going to get out?
Yes, so it could be through auto-mode execution, it could be through prefetching. It could be from multiple different threads, right, if you have fine-grained multi-threading. What lecture is this? Guys?
Lecture 18.
Lecture 18, yes. Yes. Oh, yeah, I guess you don't need to worry about that, but if you're really implementing it, maybe that the queues at the L2 level can be full, right? You may still be waiting to issue. That's right, exactly. You could have one of these for each level. Well, in main memory, I guess misses from main memory, you mean? So that is handled by somebody else, right? Which is the operating system. So you don't need to have it there. But if you have another level after main memory, perhaps. Basically, this is a structure to keep track of misses out of a hardware cache. Its purpose is to enable the operation of the cache while multiple misses are outstanding, and also bookkeeping. Yes.
Is the slide showing two tables, like a second one showing multiple misses in the same block? Is that what this is? Right?
Yes. So this is one entry, if you will, in the big miss buffer, and these are the sub entries. This is the block address that was missed. And by the way, these loads and stores are waiting for different parts in this block. So this is a single entry, and you put multiple of these together to enable multiple outstanding misses. Yes?
What's the type field for?
So type could be load or store, for example, right? Or prefetch.
So if I have like 50 bytes in the same block, will you like aggressively cancel the earlier write
Potentially. I mean, you could try to do optimizations like that. But let's not go into that right now. You could optimize a lot of things, actually, that we describe in some of these structures. This is more to give the conceptual view.
So for now, it's just like whenever I get a new thing, I just add it to the end.
Exactly. Yeah. You can think of it that way.
Take things off the top.
Maybe we'll add it to the end because isn't this
Well, added to, so I think what he meant was basically if there is an invalid entry here, you just make it valid and put the block offset.
So if you get one more request for A, do you just allocate one more? Do you have one more block?
No, not one more block, right? A means the block address.
Yeah.
If you get one more request to A, that means some other load or store is requesting it. So you allocate one of these smaller. Yeah, exactly, destination.
So you should have multiple destinations for each one.
That's right, exactly.
What if those get broken?
Well, then you cannot service that miss, right? You stall at that point.
So it's just like a circular buffer then? Because if I want to like keep the order, like if you have like 10 writes in the same location,
That's
Because if I write like 50 to D and then I write 60 to D, right, then B should have 60.
That's right. Yeah, you could do that. Although that's handled by some other structure, right? Write buffer that we discussed. But yes, you're right. You're right. You need to preserve the order.
The rat take the rat is take the rat takes care of the auto order problem.
Rats, that's for the registers, right?
Oh, yeah.
Memory ordering is done through the load store queue. Register alias table is just for the registers.
Okay, right. I meant sorry, yes.
I mean, you could integrate this with the load store queue, but let's not go into that. We haven't gone into this much detail in the lecture. I'll answer any question you have. But remember, we didn't talk about all of these things in lecture. But I'm happy to answer.
So things go into a load store queue, and then they go to this, like only if there's not some other loader or the same address. I guess I just don't understand exactly like when things get dispatched from a load store queue into this status.
Oh, into here? So load store queue. Yeah, the load store queue. It's an ordered list, a circular buffer, an ordered list of all of the loads and stores you're doing that are pending in the machine.
Okay, so then like.
And when you execute a load, you basically access the cache at that point in time. This keeps track of the misses. Okay. This doesn't keep track. This keeps track of what has missed in the cache. It's a separate structure.
Okay, so if I do like a write, that's a miss, and then I do another write to the same location that's a miss, like those two things would still make it down into this status sampling.
That's right, but you don't do the write here. Right.
Well, like we already tried, right? And we missed, so now
Okay, it came into the status handling register?
yeah.
Okay.
I guess that's all.
Okay. I don't know if I answered your question or if you answered your question, but
Yeah, that makes sense.
okay. Okay. What else? Any other questions? Other than status handling registers. Basics of a data flow processor.
Like, not like basics, but like how you do it. Whatever we need to know.
It's in the lecture notes. I'll go over. Let's see. Here, so basically it's this, right? Well, what was the idea in data flow? The idea in data flow is I have it? No, wait, it's going the wrong way. Okay. You remember the idea in data flow, right? You don't have a program counter, and an instruction executes. Instructions are represented as nodes, and instruction executes when both of its operands are ready. In fact, the instruction is fetched and executed when both of its operands are ready. Okay. Which means that the flow of the data determines the execution order of the instructions. So that's how you design a data flow machine also. You have an ISA in which instructions are specified this way. Basically, you specify what are the inputs to the instruction, and the instruction fires when both of its inputs are ready, and you also specify the destination, where the result should go in terms of the data flow graph. like which IP should be fetched, if you will. So if you look at a data flow token, if you will, the values that flow through the data flow graphs are represented as tokens. And these tokens specify which instruction and which port should they go to. Port meaning left or right operand, right? And they also generate the data. So when you execute an when you execute an instruction, it generates a token. And the token contains what is the destination of this value that the instruction produced, which is the IP, and what's the destination port. So data flow machine operates based on this flow of tokens, if you will. Right? Because these tokens will go and get stored somewhere, and an instruction, if all of the tokens of an instruction are ready, then that instruction is fetched and executed. So you can start with that. So you can build the machine around those principles, and let's look at the general principle. So basically, an instruction, when it's executed, produces a token, right? Token includes the data and the destination, and as we discussed in class, a tag. Tag is the context ID, if you will. So if you're doing a loop iteration, you can have different tags for different iterations, because you want to ensure that the same instruction in different iterations are identifiable, distinguishable from each other. So these tokens get stored in this matching area, if you will. And there's also a pool of, well, in this area there's a pool of unmatched tokens. And once here, in this matching area, you determine which are the tokens destined for the same instruction. Right? Does that make sense? Yes?
How can you know if an instruction is ready to be fetched? Because you don't know how many operands it has.
So that's also specified in the token. I didn't tell you about that, but that has to be specified, right? There needs to be some information. The assumption here was all of the instructions have 2 operands.
So
but if you have a unary instruction, then you specify that when this token arrives, you can fetch the instruction. You can have a bit saying this is unary versus binary.
So if I have a binary operand, and then one of its operands completes, now I go ahead and add it in the matching area?
Exactly. You add it in the matching area with the destination as and destination and the tag. You can find it using the destination and the tag. Another token comes. You check if there's a token with the same destination and same tag that's already waiting in this pool. And if there is one, now you have both of the operands for the binary instruction. And you can form a group, if you will. It's called the group here, which contains the tag, destination, data 1 and data 2. Destination is essentially the instruction pointer. And you go and fetch the instruction using the address of the instruction. And now you have the opcode of the instruction. You decode the instruction. And you have the data values coming from both tokens. And you also have the tag and destination. And now you can execute the instruction, the processing elements. And once you execute the instruction, now you generate a new token, which contains the data value, result, tag, and the destination. And then this flows back there. Does that make sense?
One of the disadvantages be that you cannot do prefetching because you don't know what other
So that's a good point. I don't know if you cannot is the right word, but it's not as easy as a control flow processor because basically you're not sure that your instructions are fetched in the sequential order. Right? Whereas in a control flow processor, you know that the next instruction is in the next location.
Basically, your access system memory can be the bandwidth, right? Because they only get downloaded once. Anything for that is ready.
That's right. Yes. Yeah. You fetch an instruction when that instruction is ready to execute. You guys can have food. I think we got more food, right? Or did we?
Yes, it's here.
Oh, okay. Those should be standards. I'm getting hungry too. Yes.
This is more of a general question kind of thing, but I feel that I don't know to what degree this is implemented, but to what degrees do operating systems take into account the hardware that lies below and fine-tune their performance and their behavior to match to the hardware that lies below, so that they can best utilize all the features? Because I feel there could be a good case of architectural mismatch between what lies below and what lies above, and since they do many of the same functions at different levels, there could be ways in which an operating system could hurt the performance of the processor.
That's a very general question, yes. But I mean, if you give it a specific example, it could be possible, right? The operating system can map, for example, do the virtual to physical mapping in such a way that it causes a lot of cache conflicts. Right? I think you're getting into something like that. A concrete example would be that.
Yeah.
And if the operating system is not aware of the indexing function of the cache, that could certainly happen.
Right.
And that's true. I mean, I guess you're asking to what extent do current operating systems take this into account?
Yeah.
As far as I know, not too much.
Okay. So shouldn't ideally, manufacturers of processors like say Intel or something, shouldn't they release operating system specific patches which you should apply to your system which would enhance your performance?
Well, sometimes it happens, right? Not through necessarily public channels, but through private channels potentially between different companies. So there could be optimizations that are done by taking advantage of the underlying knowledge of the microarchitecture.
Right.
Like caches is a very good example because, as we discussed today, virtual to physical mapping affects where data gets into in a cache, right? Because your indices, actually, especially in large physical caches, where a virtual address gets, where a virtual address that a program touches gets mapped to in the caches is pretty much under the control of the operating system, because your index comes from virtual address in a large cache, or mostly from the virtual address. And if it so happens that 2 pages, let's say 2 vectors you access, are mapped to the same cache set, because your virtual to physical mapping happened to be that way, then you could get a lot of cache conflicts. What else? Yes?
So back to the data flow process. So to see if I have add, then the result goes into 3 other instructions. Does it just generate 3 tokens and sort them back to
That's right. Yes, exactly. So it depends on the instruction specification. In the specification, you can say you can generate 3 tokens. That could be one thing. Or remember, actually, I think in one of these data flow graphs, we had that copy instructions, right? So here, instructions do not generate. Well, I guess here copy instruction generates multiple tokens, right? But there's always a limit in terms of how many tokens you can generate, because this needs to be specified in the ISA. Right? In the ISA, you need to specify these are your destinations. In this case, the maximum is 2. If you need to actually, if one result is used by 50 instructions, let's say, now you need to add many copy instructions to generate tokens, because in the ISA, it's probably not a good idea to specify the instruction as having 50 different destinations. Say it again? Intel style. Intel style, right. Oh, variable length? Yeah. Yeah, you could do that. I mean, you could have a variable length ISA. But then you still need support in hardware. the generation of 50 different tokens at the same time. Or that could be a long instruction, right? It takes longer to execute. What else? Precise exceptions. That's a topic from the previous exam, no? So the idea of precise exceptions is basically you want to have precise state, right? When you need to, you want to be able to return back to the program at that state when something happens. And what is the idea, notion of a precise state? Well, so let's read. The notion of a precise state is you have a program and when an instruction generates an exception, let's say you have an add, it generates an exception, your state should be as if all instructions, such that all instructions before the instruction that generate the exception have completed and retired and finished their updates to the architectural state, and no other instruction after that has been even fetched. That's the notion of the precise state. If you are able to have this precise state, now you can go and handle the exception, or interrupt for that matter, and you can, once you handle the exception, you can come back and re-execute the program, starting with wherever you left off, right? Starting with that PC. Of course, you need to save that program counter before you go into the exception, and that's the notion.
Multi-porting versus having multiple channels.
Multi-porting versus having multiple of different things, right? Not necessarily channels.
Or banks.
Yeah, banks. Okay, we can go through that too. Where is this? Do you remember which lecture it was? It's easier to go through the lectures. Oh, actually, that's fine. So what's the idea of multi-porting? Well, why do we want this, first of all? We want to be able to do multiple accesses in a given cycle simultaneously to a memory, if you will, or cache, or any kind of memory. There are multiple options to achieve this. One option is multi-porting the memory, right? Or true multi-porting, if you will. In this case, basically each cell, remember memory is composed of cells. Each cell can be accessed truly concurrently. Let me actually pull that picture. Each cell has its own different port. Okay. Where is this? Do you guys remember? It's somewhere here, I think. Actually, it's here. Oh. There you go. So that's what the cell would look like, right, for an SRAM cell. You now have two ports, if you will. You can read the cell concurrently at the same time through those two ports. That's the ideal multi-port. The advantage is truly concurrent accesses. Right? You can do two reads at the same time to this cell and get the value. Because you have two paths to read the value that's stored in this cross-coupled inversion. In this case. You could do the same thing in a DRAM cell also, right? You have multiple DRAM cell. As long as you provide multiple word lines and multiple bit lines, which are essentially your ports, you can read the data of the cell. The downside is it's expensive, right? Why? Because now you put multiple ports here, you're increasing the capacitance on these lines, if you will. You're adding more and more loading here, which means that your cell access is getting slower and slower, and more power. Remember the power equation we talked about? It's directly related to your capacitance. and it has more area, obviously.
You can't write and read at the same time, right?
You can't write and read at the same time. Yes. So you need to do this peripheral logic that we discussed in class, right? So you don't want to corrupt. Well, you could write and read. I guess depends on what kind of data will you get in the end.
Right.
But you don't want that, of course, so that's why there's some peripheral logic. So these are for two ports, if you will, left port and right port. And if the left port is requesting a write, it needs to get what is called a semaphore in this case. And it gets a semaphore such that the right port is not granted to read the request. So you need to have peripheral logic to ensure that the data you're reading is consistent. There are other ways of doing this. We discussed virtual multiporting, but that's not what you asked. So I'll skip that. We discussed multiple cache copies. Maybe this is what you meant by multiple channels. You could copy the cache or copy the entire memory and have two ports, right? This is another way of multiporting. In this case, your cell access time does not increase. Okay. You're very wasteful in terms of area, but each cell is as fast as before. You replicate it at higher level, at the memory block level, entire cache level. Now you can have multiple accesses in the same cycle. The problem is when you're storing, again, you need to store all of these. And of course, this is, I mean, if you want to have 16 ports, you have 16 copies of your 64 kilobyte cache. That's a little expensive in terms of area. So we talked about banking, right, which is a good trade-off in terms of both latency and space. And the idea is basically partition. Divide your memory into multiple banks and partition where your addresses get mapped to. In this case, for example, bank 0 contains human addresses, bank 1 contains odd addresses. I mean, we talked about many different interleaving mechanisms. Right? So now you can have, as long as your accesses go to different banks, they can truly proceed in parallel. The problem happens when your addresses happen to map to the same bank, and you're accessing them at the same time. That's called a bank conflict. In that case, true multiporting is better. Right? In true multiporting, you don't have that problem, right? At all.
But is there also another sort of way of having parallelism that you have multiple channels and you have a request on either channel? Like, I thought we had like multiple channels and then we had like different DIMMs and so I was under the impression that we had a request to like channel 0 and channel 1.
Yes, you could. You could certainly do that. The channel 0 and channel 1.
Okay.
That, again, you're partitioning your addresses in that case, right? Across different channels. And so banks are similar to those different channels. Except here, in the banks, you're really yeah, I mean, it's the same thing. That's at a different level. You'll have channel conflicts also.
So you also have like, so you also have partitioning of caches versus partitioning of memory. So the channels are partitioning of memory, but like the thing where you had two caches, partitioning of caches.
So I think at the higher level, what are we trying to do? We're trying to do multiple accesses per cycle. Right? Essentially, by interleaving or doing banking, you can do that multiple accesses per cycle. Channel is a particular instantiation of it, if you will, at the memory level. It's the same concept. You can do multiple accesses per cycle by going to different channels. And you could do multiple accesses per cycle by going to different banks.
But isn't this all assuming like that you miss all the caches? Like if you hit a cache, then you never can get to memory. So it's not a matter of the memory is restricted.
Isn't what all assuming?
So in order to take advantage of this parallelism, right? Like this is parallelism within the memory, right? So if we hit in the cache, then we'll
So okay, let's this is a cache example, but this is a general way of supporting multiple accesses per cycle in any memory. So you could design your DRAM this way, you could design your SRAM this way, or you could design your non-volatile memory, for example, this way also. Okay? So flash is organized into banks like this also. So it's a general mechanism to enable concurrent accesses. Okay? Those four things that we had described, multi-porting, it's nothing specific to caches. We discussed it within the context of caches, but these four mechanisms to remind you. True multi-porting, virtual multi-porting, multiple cache copies, or multiple memory copies, maybe we should rephrase that way, and banking interleaving, those are ways of supporting multiple accesses per cycle in any memory.
So you talked at one point about the operating system being able to choose what banks access will have to if those bank bits happen to be page numbers. So, but aren't there like lots of different banks? Like
That's right.
There's banks in the level 1 cache, there's banks
That's right.
So like, are we assuming that they're all the same bits?
Not necessarily, right? Actually, they're not on all the same bits, right? But that's a very good point. So operating system potentially affects all of those, but it may not be able to optimize for all of those at the same time. What else? Are you guys tired yet, or? Now more food. Yes.
So, I guess, can we go over again? So, you can read, you have to have multiple channels in order to do simultaneous reads, I guess. So,
From main memory,
yes. Okay, so it's the channels.
Like truly simultaneous reads.
Yes.
Because in that case, there is no shared bus across the different channels. Yes.
And then, I guess, does each, so I was doing this here, so it's, each bank has its own row buffer.
That's right, exactly.
So why do we use the channel approach for memory but not for caches? Like with a cache, we try to have it distributed. We try to replicate the blocks that are being cached between the multiple caches we have. So we improve the performance of the reads, but we don't like just have separate caches and like one cache corresponds to like half the
I
blocks
see.
of memory.
You could actually. You could use that. You could basically partition your cache and have two of those. That's true. Actually, maybe that's something to be added here.
No, just that. So memory, right? We partitioned it into.
You mean games and like the channel?
Well, channels, yeah. Right. But for the cache, we weren't doing that. Instead, we were replicating all of the blocks we were caching for all of the caches.
Isn't that because you can access caches in a single cycle, but not manually?
No, I mean it's the same thing, right? You can partition your cache into two different caches. One cache is address. It's the same as banking, basically.
Right.
In this case. Yeah.
How can it be helpful? Because you don't need to simultaneously access. Whereas using banks, you can make it the cache is single cycle operation, so why would you want access?
You can have multiple load instructions loading at the same time, right? If you have a superscalar processor or a VLIW processor.
Right. I guess the trade-off is the complexity of having to organize so much data versus having an extra cycle to worry about.
Well, but that's how our existing processors are built. You have multiple. They support multiple instructions per cycle, multiple access per cycle. Well, even existing caches like Pentium-4's L1 cache takes 4 cycles. So I don't know where you got the notion that it has to be 1 cycle, but it has to be as fast. It has to be fast. That's right. 1 cycle is desirable, but again, there's a trade-off, right? You're trying to optimize for total execution time, and if it makes sense to make your cache a little bit larger, but a little bit longer to access, And if that minimizes your execution time, because now you have a larger cache, you have better locality, better hit rate, maybe that's what you should do. And that's what designers have done in most processors today, because they want to support high frequencies. And with that high frequency, it's hard to have a single cycle cache that has very good hit rate. Yes? What else? How are you doing on time? Oh, it's a lot of time.
So the single cycle not having a digestion rate, is that just too slow? Or, I mean, too small?
Too small, exactly right. If your cycle time is, let's say, 5 gigahertz, and you want to design a cache that's accessed in 2 cycles, it cannot be large, right? You want to design a cache that's accessed in, is it 0.2 nanoseconds? Yes. 5 gigahertz. Yeah, 0.2 nanoseconds, your cache cannot be large. What else? As I said, I'm here to answer your questions. I already told you things in lectures, right? Yes?
How is the memory hierarchy organized in array and vector processors? Is it similar to this, or is there?
So we've discussed the memory hierarchy for Cray, for example, right? Cray 1.
Oh, yes.
It was essentially banked and interleaved. So it's not really different. In fact, those concepts of banking the memory came from those vector processors because they really needed the memory bandwidth in a cheap way, or relatively cheap way. So organization is very, very similar, except you need to supply a lot of bandwidth to those processors. So you have more banks usually. So if you look at a GPU today, it has lots of banks, and it has high bandwidth memory. Covered everything. Have you guys started studying? Some of you? Okay, that's good. Or is this the place where you started studying? I hope not.
Oh, the approximation of LRU.
Uh-huh. So approximation of LRU, there are many ways of doing it, right? We've discussed, actually, I think 3 ways we've discussed at least. One is, well, why do you want to approximate? Because it's hard to keep track of all those possible orderings, especially in a highly associative cache, right? With a 4-way associative cache, you could have how many orderings? 24 different orderings between those 4 different things. And hopefully you know that. And encoding that is 5 bits basically, and decoding it takes time. So, and if you increase it to, I don't know, 16-way, now how many orderings do you have? 16 factorial. That's quite a bit. And existing caches are caches with 32-way caches and processors. If they implemented true LRU, you have 32 factorial possible orderings between those blocks. That can happen. And now that becomes quickly intractable to keep track of in hardware, or even in software almost, right?
So
It'll take some time.
No one really understands.
Yeah, true LRU. I mean, true LRU is easy if you have a 2-way associative cache, right? You have only 1 bit to distinguish what is the 1 bit to tell which way is the LRU way. But as your associativity increases, true LRU becomes impossible almost. I mean, everything is possible in hardware. At what cost, though, right? So people have developed approximations to LRU. And in fact, there's another reason we talked about in class. LRU is not necessarily the best replacement policy, right? Why? We talked about random having similar performance to LRU, random replacement. You randomly pick the block you're going to replace with an set. Why? Because LRU can have bad cases. You can have crashing, if you will. Let's say you have a 32-way associative cache, and 33 elements are accessed in a circular manner, and they all map to the same set. Now you'll get a 0% hit rate. Whereas if you randomly picked 32 of those elements and kept them in the cache all the time, your hit rate would be 32 over 33, right?
Each element is a different
Block. Yeah. Each. Yeah. Well, when I talk about caches, it's all at the block level, right? Yeah. Let me rephrase that, I guess. You access 33 cache blocks in a circular manner. Cache blocks, I don't know, 0. Let's assume that these all map to the same set. I guess A, B, C, D, dot, dot, dot. I guess, I don't know, you'll need to add some numbers here. And then you access A again. And your cache is 32-way associative. So you're always missing your cache if you have this bad pattern. Whereas if you said, okay, I'm going to randomly pick these elements and I always keep that in the cache, you'll get a very good hit rate. So LRU is not the best thing, best replacement policy in terms of performance anyway. So we don't want to spend a lot of hardware on it as well. So approximations to LRU, one approximation is not MRU, right? Your policy is not to evict the most recently used block. And that's a commonly implemented one, actually. You only need to keep track of what is most recently used. And don't evict that. Otherwise, among all the non-MRU blocks, randomly pick one. There. We also talked about policies like hierarchical LRU and victim, not victim. Victim next victim, right? Yes?
Curiosity, how do you implement random?
Yeah, so you could have a randomizing function. You could have a hash function, for example, whose inputs keep changing every cycle. That's one way. It won't be, nothing will be, I guess, purely random. It'll be pseudo-random. There are other ways of doing it. You can have a shift register. It's called, I will not go into detail, but it's called a linear feedback shift register. Basically, you shift the contents of a shift register and XOR some bits within that shift register such that you get a random bit every cycle, or random register value every cycle. If you're curious, go and look it up. But you won't be tested on this, I assure you. Yes?
Can you go over the hierarchical approximation?
Hierarchical approximation. Yeah, let's go over that, I guess. I think it's easier to go over through the lecture notes. Where did we have that? Did we have it here or the previous one? Yeah, there you go. So this is the idea of a hierarchical LRU. Okay, let's see what he's talking about. Yeah, in a four-way cache, you divide the four-way set into two-way groups, if we will, and you track the MRU group and MRU way in each group. That's the idea. And I like the victim next victim better, actually, but you can look at this hierarchical LRU. And you have 2 bits for replacements for each way in the tag store. And is this the MRU group? Actually, it works better if you do 8-way, but 4 ways kind of as a generic case. And is this the MRU block within the group? And victim is always the block that is not in the MRU group, and that's not the MRU block within the group. Does that make sense? And you set the bits accordingly through the access. So for example, this shows you the initial state, if you will. This is, let's say this is your group 0. And this is the MRU group. The bits are set here, the top bits. And this is the MRU block within the group. And this is the LRU group, if you will. and these are the LRU bits within the group. If you get an access to B, basically this becomes the MRU within the group. If you get an access to D, now this becomes the MRU group. Okay?
What extra? Why do you care like what group is MRU as opposed to just what is MRU?
Yeah, I guess in this case you don't care, right? You could think about, and this is just one example. I guess in this case you have a total ordering, right? But you could think about grouping and not keeping track of within a group, not keeping track of what is LRU and MRU. Right? You just look at the MRU groups. The key idea is really grouping. Instead of keeping track of on a per block basis, what is LRU and what is not LRU, or what is the organ, you keep track of on a group basis. So you could think of other mechanisms, like you can have only designate the MRU group and only keep track of LRU within that group, and everything else could be random. So I think these become more interesting as you think of more ways, right? Let's say you have a 16-way associated cache. Right? You can divide it into 4 groups, and you could keep track of the MRU group here. And you could keep track of, potentially, you don't need to keep track of what group these things belong to, right? When something becomes MRU, you mark that MRU.
So you're just trying to avoid the reference of MRU group?
That's right, exactly. Exactly. And that's one approximation, right?
Wait, but why do you want 4 bits? Why don't you just have 2 bits that says which one of them is MRU?
You could do that too, that's right.
Because, like, here, I think the most important thing is just knowing the MRU guide. And it seems, here it's the same thing, right? We have 8 bits, but we could keep track of it with just 2 bits.
What could you keep track of with 2 bits, though?
The most recent thing you use
No, not necessarily. Well, if you just do most recently used, that's right. You just need the location. But if you need to order, you need more bits, right? And there is some ordering here, right? I'll let you think about it. That's why if you're keeping track of only the most recently used, yes, you're absolutely right. You just need 2 bits for the entire thing. But if you want to keep track of the relative order in some way, maybe not perfectly, but in some approximate way, you need more bits.
I don't see that because if you have like if you know what's the most recently used and you know which block it is, then that also know the most recently used block. So don't you like get the bigger information from the smaller?
Wait, are you thinking of keeping track of more than most recently used? I thought your question was, how do you keep track of most recently used? Right.
I guess I should ask first, like, so what is the information that's being stored here?
So the information is essentially, is this the most recently used group? And the second bit specifies, is this the block that's most recently used within the group?
Okay, but if I know that a block is most recently used, then don't I know that the group that contains that block is the most recently used block?
That's right. And that's how you keep track of that information, right?
You keep track of the other group too.
So why do I need? So like it seems to me that having all these bits isn't really adding anything. Like it seems like I could just keep track of the most recently used block, and then from there I could infer what the larger thing, like the hat in this case, that's enclosing that block. And then I would only need 2 bits.
You need to remember the other groups as well, because if it switches, you still want to like have some information about those. You don't just like switch groups to most recently used and forget everything else.
Okay, so you're saying like so here we have 2 groups, right? So here I have the most recently, let's say A is most recently used.
Right.
Right. So now let's say that D is used. So doesn't that mean that D becomes most recently used and the block that's most recently used is CD? Or is there
Yes. But then you still want to remember, like the relative ordering of A and B. Yes.
Oh, okay.
Yeah. So that you can replace.
It's all about the relative ordering, right? That's to approximate LRU. So LRU is all about relative ordering, right? You really want to know what was the relative ordering in which you touch these blocks, and that's what makes it complicated. We're trying to cut those relative orderings, if you will, that we keep track of in all of these. And that's the key idea. Like not MRU, for example. Think about it that way. Not MRU keeps track of only the MRU block. So the relative ordering is now a very partial order. MRU or everything else not MRU. LRU is a total order. Okay. And this is some order that's in between, if you will. Some partial order that we get. Okay?
How does this grouping make use of any kind of vocabulary? Or is this the kind of
Yeah, it's not, it doesn't make use of any vocabulary. Just to ease the implementation. Okay. What else? Is that all? Or last chance. I guess you guys are tired.
Is there anything you'd like to share?
Is there anything I would like to share? Study hard. Hopefully it'll be a fun exam. All right, I guess, yeah. Good luck on the exam. Prepare well.